Our oceans are basically superhighways for global trade, crisscrossed by massive ships driven by enormous, powerful propellers. But there's a hidden enemy lurking in the water, a force so powerful it can literally chew through solid metal.
Take a look at this. At first glance, you might think it's corroded, or maybe it hit a rock, right? But the damage you're seeing isn't from rust or any kind of impact. Nope. It's from millions of tiny, incredibly violent explosions happening every single second. So what is this invisible force? Okay, check out this contrast. On the left, you've got a brand new propeller. It's a marvel of engineering, ready to go. And on the right, well, that's the aftermath. The surface is just eaten away, pitted, and destroyed. The culprit behind this is a process that, believe it or not, sounds almost harmless.
It's a phenomenon called cavitation, and trust me, it's one of the most stubborn and destructive challenges in all of marine engineering. It doesn't just eat away at the metal, it also creates a ton of underwater noise, and it can absolutely cripple a ship's performance.
So to fight this enemy, you first have to understand it. That's what we're going to do now. We're going to unmask this hidden force and see what's really going on, right down at the microscopic level.
When you see bubbles forming in a liquid, your brain probably jumps to one thing: boiling. I mean, a propeller is spinning like crazy in the water, so it must just be boiling it, right? Well, not exactly.
And this right here is the key difference. Normal boiling happens when you add heat, right? You crank up the temperature until the liquid turns into vapor. But cavitation is a whole different animal. It's kind of like cold boiling. It's caused by a massive drop in pressure. A propeller blade whips through the water so fast that the pressure right around it plummets, and that lets vapor bubbles form instantly, even in ice-cold water. As one physicist explained it, the end result, you get a bubble, looks the same, but the reasons for it are totally different. One is all about heat, the other is about the physics of speed and pressure. So the main takeaway here is that we're dealing with vapor, not air bubbles. So here's our official definition. Cavitation is just the formation of these little vapor bubbles in a liquid, all because the pressure dropped, not because the heat went up. But here's the crazy part. The bubble forming, that's not what does the damage. The real destruction, the real violence, comes when that bubble collapses. And that brings us to the destructive microjet. We're about to zoom way in, to the split second that bubble dies, because that's when it unleashes its tiny but unbelievably powerful weapon.
Okay, now this is just wild. What you're looking at here is high-speed footage of a single one of these cavitation bubbles collapsing. And look closely, it doesn't just pop. As the high-pressure water around it rushes back in, the bubble implodes violent. And because it's right up against the hard surface of the propeller, that collapse isn't symmetrical. The bubble actually caves in on one side, forming and firing a microscopic jet of water. They call it a microjet, straight into the metal at hundreds of meters per second. This is our weapon. That whole insane, destructive process happens on a tiny, tiny scale. So how small of a mistake does it take to trigger it? Look at this number. 0.5 millimeter. I mean, it seems like nothing, right? But get this. A recent study found that a manufacturing defect on a propeller blade of just 0.5 millimeter, that's about the thickness of a few strands of hair, is enough to trigger severe cavitation. It can get so bad that a superyacht might have to slash its speed by almost half just to stop the propeller from screaming and tearing itself apart. And here's the absolute kicker. The current international standard for manufacturing these propellers, it actually allows for imperfections of that very size. It's like our scientific understanding of the problem has completely outrun the regulations that are supposed to prevent it. So if the standards we have aren't quite enough, how do engineers fight back? Well, that brings us to Section 3. You have to take the enemy into the lab and study it up close, inside something called a cavitation tunnel. So welcome to the front lines. This is the Emerson Cavitation Tunnel, one of the top places in the world for studying this stuff. It's basically a giant closed-loop water tunnel where scientists can create and analyze cavitation on model propellers in a totally controlled environment. And this place has a pretty amazing backstory. It was actually brought to the UK from Germany right after World War II. It's been running since 1950, and it's been constantly upgraded to stay on the absolute cutting edge of this research. Inside, it's a genuine high-tech battleground. There's a massive pump that creates these powerful currents. They use hydrophones, basically underwater microphones, to listen for that telltale acoustic scream of cavitation. They have high-speed cameras to capture those microjet implosions we saw, and they use lasers to map the water flow with pinpoint accuracy. This is where better propellers are born. So all of this incredible research, where does it lead? Well, that brings us to our final section,
The future of propellers. What does a better, quieter, more efficient propeller actually look like? The work done in places like the Emerson Tunnel has led to some really amazing designs.
One of the most successful solutions so far is what's called the skewback propeller. You can see how the blades are swept back in this really dramatic curve. This complex shape lets the blades slice into the water more gently, which delays that big pressure drop that causes cavitation in the first place. This design is a huge reason why modern submarines are so incredibly stealthy.
The skewback is a brilliant evolution, for sure, but some engineers are pushing for a full-on revolution. What if a propeller didn't even need tips at all?
And this is the result, the toroidal propeller. It's a closed-loop design that looks like something straight out of science fiction, but what's wild is that the concept is actually over a century old. By turning the blades into this continuous ring, it spreads out the hydrodynamic forces, and that dramatically cuts down on the vortices at the tips, which are a huge source of both cavitation and noise.
And these aren't just cool science projects. The stakes here are huge. Studies show that a staggering 80% of all the noise a ship radiates underwater comes directly from its propeller. So making them quieter isn't just about efficiency or being stealthy. It's about protecting entire marine ecosystems from noise pollution. You know, we've gone from the simple Archimedes screw to these silent, unbelievably complex rings. The propeller has been constantly evolving. And as we keep pushing for a quieter, more efficient world, it really makes you wonder, what will the next great leap in marine propulsion even look like?